All right, hi everybody. Again, welcome back. This is Brett. I'm going to be continuing with our sample session here, working on IB Physics higher level. Okay, a couple example questions. As usual, if you feel that I'm going too fast or need to pause me for some questions, just feel free to let me know. With that, we'll get straight to it. Okay, so this first question is going to be a little bit conceptual, as is the rest of this whole physics section, to be honest. There's a few conceptual questions. The first thing that they're asking is they want us to define electric field strength, okay? Now, as we all know, the electric field originates from an object or a particle that is charged in some way, right? It's either positively charged or negatively charged. And the strength of the electric field is going to depend on two things, right? It depends on how strong the charge or the magnitude of the charge, basically big Q, is of the object or the particle. The second component to it is also how far away we are from the charge, right? So if you remember the equation, it's kind of like a Q over R squared business. So those are the two big variables that are going to be affecting the electric field strength. So this time I've actually kind of pre-written the English portions of the conceptual questions, just to save some time, right? So they originate from any charged particle, right, which will exert an electric force on any particles. So that's pretty key. The reason scientists discovered the electric field in the first place was they found that a charged particle would exert a force, an electric force, on other particles that were around it, okay? So we've got the magnitude and the distance away from the particle. And we also want to recall or remind them that vectors will represent the electric field direction and strength. Now, this next question has a more of a quantitative approach to the situation here. We've got protons traveling with a very fast velocity, 3.9 times 10 to the 6th meters per second, into a region between two charged parallel plates, X and Y. So this would be causing an electric field, since we have a fully positive plate at the top. Plate Y is grounded to the bottom. That means it'll have no charge whatsoever. So it's a pretty simple situation. Because we have a positively charged top plate, we have electric field lines pointing downwards, right? And these protons are traveling exactly in between these parallel plates, and they are apparently not deflecting at all, right? So if we also have a uniform magnetic field, categorized by big T, right? That's also in this region between the plates, and these protons are actually going straight through without any deflection, okay? We want to know how could that be possible, okay? We want to know what is the state of the magnetic field. In order for this to be possible, well, as you can probably guess, the force caused by the magnetic field is going to have to cancel out the force that is pushing down these protons away from the top plate. So if the plates were just there on their own, these protons would actually be moving downwards. So maybe I can use a pen here, right? We've got this electric field pointing downward, and this would cause the protons to actually move away from that positive charge, right? But they're not doing that because of this magical uniform magnetic field. The fact that these things are uniform is very good news, because these are just straight lines that we're dealing with, right? So in order for that magnetic field to cancel out the electric field, it would have to push in the opposite direction. So it would have a force that's pushing upwards. We can say that this is blue, magnetic field pushing upwards to cancel out the electric field, right? And so in order for us to understand the direction of the magnetic field, it's a bit of a trick question, because magnetic fields and the forces resulting from them actually follow the right-hand rule, okay? So since there's a perpendicular nature to the situation, unlike electric fields, which is just 1D, right? We've got a right-hand rule. We've got three vectors on our right hand. Index finger represents velocity of our particle. Middle finger is going to represent what? The direction of the magnetic field B, big B. And then the thumb is going to represent the force produced by the magnetic field, okay? So all we got to do is stick our hand out. We know which way the protons are going. The protons are going exactly to the right. We know which way the, sorry, you can't see me here. We know which way the forces must go, that is upwards. So which way must the magnetic field be pointing? It must be pointing into the page, right? This is a X, Y, Z coordinate plane here. So the Z direction would be the, I think that's negative Z direction, okay? So we would have something like this, pointing into the page in order for the force to cancel out the electric force, okay? So once again, I've written that out in pretty clear English here, hopefully. We do want to recognize they move away from the positive plate, right-hand rule. Just recognize what each of the fingers represent in terms of the vectors, and the rest should kind of work itself out. Okay, let me know if that makes sense. Now, to keep things moving here, they are actually providing us with the strength of this magnetic field. So we're actually going to be doing some calculations here, so maybe I should whip out the pen. They've already given us the velocity of these protons, so let's write that in already. So Vp equals, from the previous slide, that is 3.9 e to the 6th meters per second. Okay, this is a 9, not a 4. Okay, and then now they're giving us the magnetic field strength, which is basically capital B with the vector, and that is 2.3 e to the negative 4. I'm using the e notation because that's easier for your calculators. Obviously, you will be using a calculator for these problems. We're dealing with very large and very tiny numbers. And we want to know what should be the electric field strength between the plates. So already we know that the forces must cancel, right? So the F's must cancel, aka be equal to each other, right? So cancel, and you know, in all of physics that translates to these forces must be equal to each other, right? And so we have force electric, and then we have force magnetic, okay? So force magnetic, we can actually call that FB. That is represented by our QV big B, and actually a sine theta, although we will not really need to use that in this case because we have a perpendicular situation. And then force electric is just QE, magnitude of the electric field, okay? So what the question is asking us here is we want to know what is the magnitude of the electric field between the plates, and also the right units, okay? So essentially, if these forces must cancel out, we basically want to set these two values equal to each other. So I think I can do this on the same slide. Let's just wipe out the stuff at the top here. And notice just from the beginning that our Q values are going to cancel out, right? So if we set this equal to this, right, those Q's represent the same thing, that is the charge of the proton, right? So they're not the Q's of different variables, so that makes things very easy for us. And we can just simply set this as E equaling, VB, and like we said earlier, our angle here is actually going to be 90 degrees because the direction of our velocity is straight to the right, and the direction of our magnetic field is straight into the page. That makes it a perfect right angle, perfect 90 degrees, and sine of 90 is going to be 1, so we can actually kind of ignore that stuff, right? So really this problem ends up becoming quite easy. So it's just going to be velocity times the magnetic field strength, that is 3.9 e to the 6th times the 2.3 e to the negative 4, okay? And we're just going to do that calculation, erase the rest of this drama over here. Okay, and if you stick this into your calculator, you should get something around 897. And the units for an electric field is usually newtons per coulomb. I don't see why that would not be the case here. Some of you might be thinking, like, I think Volts per meter is another possible units, but we don't necessarily need that here. So just about 900 newtons per coulomb would have to be the strength of the electric field. Any questions there? All right, good. All right, next up is part B, which is moving on to the photoelectric effect, and I'm going to try to keep things moving here. In this case, we have light, monochromatic incident light, striking a metal surface, and as a result, the electrons are going to be emitted instantaneously from the surface of this metal, okay? So right off the bat, you should be recalling a few simple equations that revolve around photoelectric effect. And you should also keep in mind that electrons are not always necessarily emitted just because we have some incident light of a specific frequency, right, monochromatic, striking it, right? So what this tells you is that the light must be of a wavelength that is short enough to have enough energy to emit electrons from the surface of this metal, okay? So this question is asking us a couple conceptual questions, okay? We want to know, why is the emission of the electrons instantaneous? Now you might be thinking, how could it be any other way? Well, this question is really asking us about the difference between the wave-like nature of light and the discrete packet nature of light. So most people back in the day thought that light was a wave, right? And if light was a wave, it would deliver its energy gradually to the electrons on the metal surface, right? Now the reason why the electrons are instantaneously leaving the surface of the metal is because the photons in this case are actually discrete packets of energy. So what they're testing us on is, do you recognize that there is a quantized model for light, which would cause the energy from the photon to be delivered to the electron fully, right? So each individual electron is absorbing a photon's energy all at the same time. It's not gradual, and therefore it will emit at the same moment that the photon strikes the surface, okay? So we want to perceive light as discrete packets of energy according to the frequency of the atom. So the energy of each photon is going to be related to its frequency, okay? And so instead of energy building up on the surface of the metal, it's actually just going to be instant. The moment these photons strike the surface and have enough energy to disroot a electron, it's going to do so, right? So hopefully that makes sense. The next part is asking us, why does the energy of the emitted electrons not depend on the intensity of the incident light? So, like we said before, the frequency is really what dictates the energy of a photon, right? So we have the Planck's equation, something about energy equaling Planck's constant times the frequency. That is basically what the energy of the photon is, right? It'll only depend on the frequency. When we talk about intensity, intensity is like the amount of photons that strike the surface. So, or rather the number of photons that are emitted per second, right? Now, if we increase the intensity, or rather the number of photons that are striking the surface of this metal, sure, more electrons will actually be dislodged from the metal surface. But does the energy of those individual electrons necessarily increase just because there are more photons? Not really, okay? So even though we've got a ton of more electrons leaving the surface, they will actually still have the same amount of energy per particle as the photons did in the first place, okay? So again, we want to make the distinguishment between energy and number of electrons. Yeah, right. So there's going to be a separate equation for intensity and number of photons or number of electrons that will dictate this behavior. Okay, and we'll get into that a little bit later. So any questions or misconceptions about the photoelectric effect, let me know now. If not, we'll get into a more calculating question. All right, so what we're going to get into now is actually a quantitative physics problem that revolves around the photoelectric effect. Like I said before, the equations governing this are generally pretty simple. You just have to kind of stack them on top of one another. So now they're telling us the wavelength of the incident light, as well as the work function of the metal, okay? In case you forgot what work function meant, this basically is the minimum amount of energy required to dislodge an electron from this particular metal, okay? So different types of metals are going to have different work functions because, you know, dislodging an electron from a different type of metal is going to require different levels of energy from these photons, right? So let's start rewriting what they've given us. We do want to convert things to units that make sense. So wavelength, we're going to go ahead and jump straight to 420 e to the negative 9th for nano, meters for meters there. And then the work function, the symbol for work function is like that. Your textbook might be a little bit different, but we just want to distinguish them here, this negative 19 joules. And all they're asking us for here is the kinetic energy of an emitted electron. Now, so this is going to be like a energy conservation type of situation. So quick review, the energy that a photon has as it strikes the metal must equal the combination of the work function. So the work function is the energy that is kind of taken away from the photon by the metal, and as well as adding on to the kinetic energy that the emitted electron has, okay? So the emitted electron is not going to have the same amount of energy as the photon. It's going to have the energy of the photon minus whatever it lost in the collision, aka the work function, okay? So our raw equation for the energy of a proton is going to be E, let's say proton, must equal the kinetic energy of the electron, for example, plus the work function, okay? And in this case, we just want to know what is the energy of a proton, right? So we are going to eventually need the frequency of this light, okay? So energy, as we know, is actually going to be Planck's constant times the frequency of that proton, okay? And that is going to equal kinetic energy electron, which we don't really, that's what we're going to calculate, so we don't need to expand on that, plus the work function, which we already have. Now, since we're going to need the frequency of this photon, we can actually convert this, right? We've had the, you know, the universal equation, which everybody knows by 9th grade, is velocity of the speed of light, sometimes referred to as just c, is going to be the wavelength times the frequency, okay, of this photon. And if we want to solve for frequency of this photon, let's just say like this, we'll have to divide that out. So Vc, the speed of light is always going to be fixed at 3 e to the 8th, okay, meters per second. And then I'm dividing by the wavelength, which is in meters, it's going to be 420 e to the negative 9th, okay? Now, if you plug that into your calculator, okay, you should get something like 7.15 e to the negative 14. And that's going to be in hertz. Oh, sorry, that's not negative. That should be positive. Okay. And that's going to be in hertz or seconds to the negative 1. You can stick that in there. And we're going to use that value when we find the energy of the photon and then later the kinetic energy. All right, so let's try to wrap up this problem then. Again, we had actually found the frequency of the photon. And we're going to plug all of this into our grand equation here. So remember, we still need to multiply this frequency by the Planck's constant, which is h. And our h is going to be 6.63 e to the negative 31 times this frequency, which is 7.15 e to the 14th. And that's all going to equal the Ke. plus the work function, which is already given to us in the units of joules. So that is 3.4 e to the negative 19, okay? Now, I'm not going to go through the algebra with this. Obviously, you just multiply out those two terms on the left, and you have to subtract the 3.4 e to the negative 19 from that, and you will finally get the kinetic energy of the electron. Let's have this subscript here as 1.3 e to the negative 19, and of course we need the joules. Oops, joules. That might seem very tiny, but when you take into consideration the mass of these electrons, you will find that the velocity is actually extremely large. So I would feel very confident about this final answer. Okay. Any last minute questions on how we got there? If not, we'll go to the final problem or section of this problem. All right, so now we've got a problem that's a little bit more heavy on the math. Right off the bat, it's giving us dimensions, right? So an area of a piece of the metal. It's giving us the intensity of the light on the surface, and it's also telling us how many electrons are emitted for every 300 photons. We want to know what is the electric current that leaves the metal's surface. So there are definitely multiple layers here, and we'll go through each one of them, although the equations that are involved are not too complicated. So right off the bat, you want to say that we know that we're going to need the area, right? So the area is going to be 1.5, and again, we want to convert this to meters, negative 3, 1.5, and then the 2.0, e to the negative 3, and that will give us an area of 3 e to the negative 6th meters squared. Now, why is that important? The intensity that it gives us is actually a watts per meter squared, right? So this is an intensity on a per meter squared basis, right? So that's based on the area, right? So that's going to be 4.5 e to the negative 6th. Okay, that's watts per meter squared. Whoops. Used to writing seconds squared, okay? Meters squared. And also keep in mind, so one electron is emitted for every 300 photons. That's going to be like per second, because electric current is also a per second type of unit, right? So keep in mind that the watts is actually joules per second. So in case you're worried about the rate of current or whatever, just be aware that the watts already has the per second business built into the problem. So you do not need to worry about that, okay? And then we also care about the number of electrons, so we can designate that as Ne. That's going to be, one is going to leave for every 300 number of protons, okay? So that is a relationship that we're going to keep in mind towards the end, because all of the variables that we have now so far are pertinent to the photons, okay? So we're going to first find the amount of protons that are leaving the surface, then convert that to electrons using this factor, okay? Now, what is the core equation? I'm going to try to squeeze in a bit more here. What is the core equation that surrounds the number of protons that leave a surface? That's going to be number equals the intensity, okay, over the energy of each individual proton, okay? And we're going to have to just convert a few things with this equation in a little bit on the next slide. All right, so we're going to go ahead and simplify this equation just a little bit. We recognize that the I that we want is actually kind of like a total intensity, but what they gave us was an intensity per meter squared, right? So we're just going to have to multiply that out by the area that was given to us, which will cancel out the meters squared, giving us a raw wattage, right? So this is actually going to be IA times the area over the energy of the photon, okay? And can we plug in some numbers here already? I think so, right? We've got our IA, which is 4.5 e to the negative 6th times the area, which is already found. That was 3e to the negative 6th. Okay, and we also had already found the energy of a photon from the previous example, so we can just reuse that. That's the beauty of these multi-layered questions. 4.7 times 10 to the negative 19. Okay, and if we plug that all into our calculator, we're going to find that the number of protons that are leaving this situation is 28 e to the 6th, okay, per second. Pretty crazy, okay? Now, be aware that we do want the number of electrons, okay? So how can we put this? We can say number of electrons must equal 1 over 300 times the number of protons, which is what we had already on the previous slide. So we can plug that right in here, 28 e to the 6th, okay? And if you plug that into our calculators, we're going to get a more modest 94,700 electrons leaving the surface of this metal every second. Okay, so we're getting closer. Just keep in mind they're actually asking for the electric current that's leaving the metal surface. So what was the equation for current? Let me actually just wipe all this out for us. Might take a second. Oops. So current is actually charge per unit time, right? So again, this is going to be in I. Oops. Current is charge per unit time. Okay. And honestly, our per unit time is already per second, so we don't really need to worry about that t business. We can set that equal to 1. But the total charge is going to be the number of electrons times the charge of each individual electron. Okay? That is AKA the charge of each individual electron times the number of electrons. We should hopefully have already memorized the charge of an individual electron. That is 1.6 e to the negative 19th. And what is the number of electrons that is leaving the surface of this metal? It is 94,700. Okay. So after carrying out that very simple multiplication, we've got how many amperes? 1.5 e to the negative 14 amperes. Okay, and then we would be done with this question. Okay, so as you can see, this is a very multi-layered question, but the individual components, the individual formulas that are used are not very complicated. You just have to be not very intimidated by what the question is asking you. You might think that electric current is so far removed from the photoelectric effect. But as long as you keep the equations in mind and try to simplify things in your mind, you'll be able to get those creative juices flowing fairly simply, fairly easily, and end up at the right answer. Okay? So are there any last-minute questions before we wrap up this session? All right, if not, that'll be it for today's sample session. We did go quite over time, but hopefully you all enjoyed. We got through the entire thing.